Hi, this is week 26 of AP Physics and we're studying torque and rotational motion. For this lesson we're going to look at torque and angular acceleration as well as torque and inertia. For our student objective says students will learn the relationship between torque, inertia, and angular acceleration. Let's begin our conversation by discussing torque and angular acceleration. So in the slide it states that when a rigid object is subject to a net torque, it undergoes an angular acceleration that is directly proportional to the net torque. What that means is as the net torque increases, so does the angular acceleration and vice versa. That's what they mean by being directly proportional to each other. Either they both go up or they both go down at the same rate. Next, let's discuss moment of inertia. Symbol for moment of inertia is I, and that is a measure to an object's resistance to a change in angular acceleration. So if you have an object that's stationary, it's at rest, and you want to go ahead and get it spinning, you're going to have to put a lot of force to get it to spin. But once it's spinning, you're also going to need a lot of force to get it to stop because it resists change. Initially it was at rest, and you're going to need a lot of energy to get it from rest to spin. But once it's spinning, you're going to need a lot of energy to once again bring it back to rest. Now the formula for moment of inertia, it is I equals m times r squared. Now that's not the only formula for moment of inertia. It actually depends on the shape of the object. So that formula we just discussed is really for this. On the top right corner, we have a cylinder that is all the mass is on the outside and it's hollow on the inside. So the formula for moment of inertia would be mr squared. M is mass, r is the radius. Next, what if the cylinder was solid all the way through? The formula would change. Now it would be 1/2 mr squared. Next, what if you have a long rod and you're spinning it around its center? Well, the formula for that would be 1/12 ml squared, where the L is the length of the rod. Now going to the top right corner, we have a solid sphere. So solid all the way through. Now be 2/5 mr squared. What if we had a hollow sphere, something like a basketball, where most of the mass is on the outside and inside it's just air, so very little mass at all? That'll be 2/3 mr squared. And finally, what will be the moment of inertia for a rod that's being spun along its end? So it'll be 1/3 ml squared, where again the L is the length of the rod. Now we're going to go ahead and derive a formula for the relationship between torque and inertia as well as angular acceleration. And we're going to go ahead and derive it using Newton's second law. So here we have force is equal to mass times acceleration. We're referring to tangential acceleration here. And the first thing we're going to go ahead and do is multiply by r. And once we do that, we have r on the left, r on the right. Now we're going to go ahead and substitute the tangential acceleration with r times angular acceleration. So it'll give us this formula here. There's a substitution. Next, we're going to go ahead and substitute for the torque. So force times the radius will give us the torque. So that's what you see right there. And the last substitution is going to be I for inertia, which is mr squared. So now mr squared is substituted by the I. And there's our formula. Torque is equal to moment of inertia multiplied times angular acceleration. That is a formula we're going to go ahead and use in some of the examples that are coming up in our lesson. And next, angular acceleration of a rigid object is proportional to the net torque acting on it. So we're going to go ahead and have, if you add up all the torque acting on it, so you get the net torque, will give you to the inertia multiplied times the angular acceleration. So we have I is equal to the moment of inertia of each one of all the points in a solid disk. All right, so it behaves as one object. All right, so we're going to go ahead and now do some examples, and we're going to go ahead and solve for moment of inertia problems. Let's take a look at example 4. Here we're asked the following question. In an effort to be the star of the halftime show, a majorette twirls an unusual baton made up of 4 balls fastened to the end of very light rods. Each rod is 1 meter in length. So they ask you find the moment of inertia of this baton. All right, now the mass for each one of the spheres attached to the end of the rods is given where the 2 orange spheres, it's a mass of 0.2 kilograms, and the 2 blue spheres have a mass of 0.3 kilograms. So that's given to us. Now, moment of inertia for this formula, notice that the mass is on the outside, no mass on the inside as it twirls around. It's going to be the following. Inertia is equal to mass times radius squared. Radius from where the axis of rotation is. In this case, this will be the axis of rotation. All right, so if the rod is 1 meter long, then therefore the length from the axis of rotation is really just 0.5, half of the length of the rod. So that's going to be the R we're going to use for each one of these. And notice that they're labeled 1, 2, 3, and 4. So we're going to go ahead and label them the same way as I go ahead and solve for, in this case, part A, what is the moment of inertia of the whole baton setup. So for number 1, it's going to be the mass, which is 0.2 kilograms, multiplied times R, which is the radius of 0.5 meters squared. For number 2, it's going to look very similar, except that number 2 has a bigger mass of 0.3 kilograms. It's going to be multiplied times the same radius. Number 3 is going to look identical to number 1, since number 1 and number 3 are the same mass, 0.2 kilograms, and the same distance. And finally, number 4, which is right here, the blue sphere right there, it's going to be the same as number 2. They match each other. So it's going to be 0.3 kilograms multiplied times the same distance of 0.5 squared. Now we're going to go ahead and plug these into the calculator and get our answer. All right, so for the number 1, it's going to be 0.2 multiplied times 0.5 squared. It's going to be 0.05 kilograms times meters squared. Now that's going to match number 3 because it's the same mass and the same distance. So I just write that answer. And now number 2 is going to be 0.3 multiplied times 0.5 squared. Gives us 0.075, which matches also number 4, 0.075 kilograms times meters squared. You want the total for this setup. Well, just add them together, and that's going to give us our answer. So it's going to be all those values added together. It gives us a grand total of 0.25 kilograms times meter squared. So that will be the answer for part A of example 4. Now let's go ahead and take a look at part B. In this scenario, now they go ahead and the majorette's holding it though from one end. So the majorette is spinning. Try spinning the baton as shown. Calculate the moment of inertia of the baton. Now the axis of rotation is now here rather than before where we went through the center. All right, so now the orange spheres are no longer part of the formula. And the reason why they're not is because, well, although they still have a mass, they no longer have a radius because they're right on the axis of rotation. So therefore, only the blue spheres are really used to figure out the moment of inertia. All right, so I'm going to go ahead and do that part B right here. And for that one, what it will look like, it'll look just like 2 and 4 right here. So I'm going to go ahead and write those down again. But it's the same formulas. 0.3 kilograms for each of them. 0.3 kilograms. And they're both at the same distance of 0.5 meters squared. So that's going to go ahead and give us what we had up here, 0.075 kilograms times meters squared for both of these. So put it together. Now what's the new moment of inertia? Total for that setup. That's going to be both of these added together, and it's 0.15 kilograms times meters squared. So that's the answer for part A and B of example 4. Now let's go ahead and move along to our next problem. In this one, problem number 10 says, if one of the rods is lengthened, which one would cause the largest change in moment of inertia? The vertical rod or the horizontal rod? All right, so right here, the vertical rod or the horizontal, vertical going up and down, if we extend it, again, it has no radius, so it wouldn't really change the moment of inertia. It would be the horizontal rod. If we were to elongate that, then that's going to increase the radius and it's squared. So that will definitely have a large change in the moment of inertia. So it will be the horizontal rod. All right, let's go ahead and move along to problem number 11. And this one says, another baton is created by making 4 identical balls, each with a mass of 0.3 kilograms. So all of them have the same mass, and fixing them as before, except that one of the rods has a length of 1 meter and the other one has a length of 1.5 meters. Calculate the moment of inertia of this baton A, in part A, when it's oriented as it is in example 4. Now, for example 4, I'm going to assume that because they had us spin it 2 ways. Here's in part B, they had it from one end, but in part A, they're spinning, and here's the axis of rotation. I'm going to assume that they're referring to this rotation when I'm answering that question. So they're spinning it from the center. All right, so let's go back to the problem. And a drawing is always good. Helps me visualize what's going on here. All right, so we're going to have one rod that is longer than the other. And here we go. And for the longer rod, it has a length of 1.5 meters. So if first this is the pivot point, the axis of rotation, then one side, that's going to be our R, that's going to be just really 0.75 meters, and the other one, same thing, 0.75 meters. For the shorter rod, which is a 1 meter total length, this is going to be 0.5 meters, and the other one's going to be 0.5 meters as well. All right, now at the ends, you'll find all of them identical spheres, and all of these spheres are going to have a mass of 0.3 kilograms. So that's given to us. So now we're going to rotate it with the axis of rotation being here in the center, and they ask us figure out the moment of inertia for this problem. All right, so let's go ahead and do that. And for the moment of inertia, we're going to solve for each one of these. We're going to label them. Let's label this one 1, 2, 3, and 4, so you know what I'm talking about. All right, and let's start with number 1. Moment of inertia is going to be I1. It's going to be the mass, which is 0.3. All of these will have the same mass. Multiply times the distance from the axis of rotation, which is 0.5 meters squared. Moment of inertia of the second one, all of them have the same mass, 0.3, but it's that's a longer rod, so it's 0.75 meters squared. For the third one, will look identical to the first one, since they're opposite each other on the rods. And the fourth one will look just like number 2, all of them with the same mass, but a little bit longer length of 0.75 meters from the axis of rotation. All right, from there we go ahead and put it into the calculator. So it's going to be 0.3 times 0.5 squared. It's going to give us 0.075 kilograms times meter per second. Same for number 3. Now for number 2 and number 4, it's going to be 0.3 multiplied times 0.75 squared. I'm going to round it off slightly, 0.169. Now, we want to get the total inertia. We're going to go ahead and just add them all up. Inertia total is going to be, put all of these together. And it gives us an answer of 0.488. And that's going to be our total inertia for part A of this problem. This is problem number 11. Next, let's go ahead and take a look at part B of this problem. And part B says, what if we orient it as we did in problem number 10 with the axis being the short rod? All right, that's the one where the person was holding it from the end, and there's a short rod, so it's spinning like that. What's the new moment of inertia if we spin it in that direction? Again, if the axis of rotation is going straight down and I'm holding it on my finger, really these two have no radius, only these two do. So though they have a mass, they have no radius, so therefore they have no inertia for number 1 and number 3 there. So to figure out what would be the new moment of inertia, all we have to do is get rid of number 1 and 3, and let's go ahead and do that. So there goes number 1, and there goes number 3, and now we can just go ahead and add both of these together to get the new moment of inertia. So it's going to go ahead and be 0.169 times 2. It's going to give us 0.34 or 0.338. And that is our new moment of inertia for part B, if we have the axis of rotation going down the smaller 2 rods. Next, let's go ahead and move along and talk about torque and inertia. So the relationship is as follows. It says the moment of inertia of a hoop is calculated by imagining that the mass of the hoop, which is uppercase M, is divided into nth amount of small segments having masses M1, M2, M3, and so on, all the way to get to Mn. Next, all the segments around the hoop are at the same distance r from the axis of rotation. So we can drop the subscripts on this distance and more or less say that m1 plus m2 plus m3 is equal to just uppercase m. So there's our formula for moment of inertia. Quick reminder though, that formula is only for a hoop where most of the mass is on the outside and there's no mass in the middle. But depending on the shape of the object, then you're going to go ahead and have different moments of inertia. And this is again a review right here that, yeah, the moment of inertia varies. So this is on the top left, the classic formula for moment of inertia if the mass is on the outside. But if it's a solid cylinder, it'll be this formula, a rod here on the left and right rods. And for spheres, if it's a solid sphere versus a hollow sphere, those would be the formulas of inertia. And you'll notice that what changes is the fraction in front of the mass. Also worth reviewing, there is a relationship between linear motion and the motion for a rotating object. So you can see right here, for our first formula for velocity, and angular velocity is more or less the same formula, except that velocity is replaced with angular velocity and acceleration is replaced with angular acceleration as well. Same you can say for displacement and angular displacement. Here again, velocity versus angular velocity. Those are all share common characteristics. Also worth reviewing, velocity for tangential velocity is equal to angular velocity multiplied times the radius, and tangential acceleration is equal to angular acceleration times the radius as well. All right, all those formulas will come in handy for the examples we're going to go ahead and work on next. Let's take a look at example 5. And this one says a baseball player loosening up his arm before a game tosses a 0.15 kilogram ball, only using the rotation of his forearm to create the acceleration. So from here, he would hold his arm steady and just use the forearm. It says the forearm has a mass of 1.5 kilograms and a length from the elbow to the ball center of 0.35 meters. The ball starts from rest and is released with a speed of 30 meters per second in 0.3 seconds. So now the first question we're asked is find the constant angular acceleration of the arm and the ball. All right, so to do that, we're going to go ahead and begin with the velocity of the ball. So it's going to be the velocity is equal to initial velocity plus acceleration times time. Now for acceleration, how we relate that to angular acceleration? Acceleration, in this case tangential acceleration, is equal to the radius times the angular acceleration. So we're going to modify this a little bit. By the way, initial velocity is 0, so I'm going to leave that out. And I'm going to put alpha times r times t. Again, tangential acceleration is equal to the radius times the angular acceleration. So I substituted the a for that. VO, the initial velocity is 0, so that's why we left it out. All right, now I want to figure out what is our angular acceleration. I'm going to divide both sides by RT. So our formula becomes this, velocity over r times time. All right, so this will be part A. Let's go ahead and plug in the values. We know that the velocity is 30 meters per second. I want to divide it by r, which is the length from the elbow to the center of the ball, which is 0.350, multiplied times the time. It only took 0.3 seconds. All right, so we just plug that into the calculator. 0.35 times 0.3, that's the denominator, is 0.1. So it's going to be 30 divided by our denominator. So it's going to give us 286 rads per second squared. That will be part A, the angular acceleration for the ball. All right, let's go ahead and move along to part B. In part B, they ask you to calculate the moment of inertia of the system consisting of the forearm and the ball. All right, so moment of inertia. All right, for this problem, first of all, we need to separate the two things that are accelerating here. There's the ball, that's one, and for the moment of inertia of the ball, it will be 1/2 m times r squared. But for the forearm, it's a different one. It will be treated as a rod. So now we got to go back a little bit, do a little bit of review, quite a few slides, and there we go. And it will be this formula right here. For L is the length of the arm, and it's at the end of the rod. So it will be 1/3 m times L. So this will be for the moment of inertia of the A for arm, B for ball, and that's going to go and be 1/3 ml third to the, pardon me, second power, where L is the length. All right, so we're going to go ahead and calculate the moment of inertia for the forearm and the ball, and then put them together to get the total moment of inertia for the system. All right, so let's plug in the values. The mass of the ball, in this case, is going to be 0.15 kilograms, and that's going to be, the distance is going to be 0.35 meters, so we're going to go ahead and square that, get the answer for that. 0.35 squared multiplied times 0.15 gives us 0.018, and for the forearm it's going to be 1/3 that's mass, which is 1.5 kilograms, multiplied times the same distance, 0.35 squared. So it's going to be 0.35 squared multiplied times 1.5 divided by 3. It gives us 0.061. So now we want the total moment of inertia for the whole forearm and the ball system. We go ahead and we add them up. So it's going to go ahead and give us 0.079 kilograms times meters squared. That is the total moment of inertia for the ball and the forearm put together. That takes care of part B. In part C, they ask us the following. It says, find the torque exerted on the system as that results in the angular acceleration found in part A. So what will be the total torque? All right, so that's going to be torque is equal to I, the inertia, which we just got over here, and we're going to go ahead and multiply that times the angular acceleration. All right, that's going to go ahead and go as the torque. So it's going to be 0.079 for the inertia, and we're going to go ahead and multiply that times the angular acceleration, which is 286 rads per second. All right, and we're going to go ahead and solve for that one, multiply them together, 0.079 multiplied times 286, and that's going to give us a complete torque of 23. It's going to be newtons times meters. All right, and that takes care of example 5. In problem 12, we're asked the following question. It says, why do pitchers step forward when delivering the pitch, and why is timing important? Well, as the pitcher steps forward as they deliver the pitch, then while their movement forward is going to create momentum from their body, and they can transfer that into the balls with additional speed. All right, so that's the reason why I step forward, to create more momentum. Why is timing important? Well, that peak momentum, the maximum momentum, only lasts for about a fraction of a second. So you want to release the ball when you have maximum momentum. All right, that takes care of problem number 12. In problem 13, we're going to go ahead and solve the following question. It says, a catapult with a radial arm of 4 meters in length accelerates a ball with a mass of 20 kilograms through a quarter circle. The ball leaves the apparatus at 45 meters per second. If the mass of the arm is 25 kilograms and the acceleration is constant, A, find the angular acceleration, B, find the moment of inertia of the arm and the ball, and C, find the net torque exerted on the ball and the arm. All right, so let's go ahead and work on this problem out. Again, outlining what we have the length of the arm, we have the mass of the ball, we have the mass of the arm, velocity initial and velocity final of the ball as it leaves the catapult, and they did say through a quarter circle. So we do have the angular displacement, which is 90 degrees, and we don't need it in degrees, though we need it in radians. So if a full revolution, a full circle is 2 pi, then a quarter of a circle, which is 90 degrees, will be a half pi rad. All right, so that's what we're going to go ahead and use for our angular displacement. Now, formulas, first of all, letter A, they ask us find the angular acceleration. So that's going to be our first goal. Find the angular acceleration. So we're going to be looking for this alpha right here. So we need to isolate it. All right, so we're going to go ahead and do that. All right, so let's get to work on this formula. First of all, the initial velocity was 0, so you can go ahead and ignore it. So it's going to be angular acceleration is equal to 2 alpha multiplied times the angular displacement. I want to go ahead and divide by 2 and the theta on this side. So we're going to have, all right, that will give us the angular acceleration. Next for us, all right, we're going to go ahead and get, how do we get this velocity? It's tangential velocity here. Tangential velocity is equal to R multiplied times the angular velocity. So I'm going to go ahead and divide both sides by the r. So there it is. Angular velocity is tangential velocity over radius. Alright, so we're going to go ahead and plug that in here. So it's going to look like this. Tangential velocity over the radius squared over 2 multiplied times the angular displacement, and that is our angular acceleration. Alright, so let's go ahead and plug in all these values, and ideally we should be able to move the 2 down here. So let's rewrite it a little bit neater. Velocity tangential square over 2 angular displacement multiplied times the radius squared. Alright, so that looks a little bit better. Plug in the values. So it's going to be initial velocity of 45 meters per second. That's going to be squared divided by 2 times the angular displacement, which is 1/2 pi rad. And finally the r, which is the length of the arm, which is going to be 4 meters, and that is squared. Alright, so we're going to go ahead and plug all of that into a calculator and get our answer. So it's going to be, let's see, 2 multiplied times 0.5 multiplied times 3.14 times 4 squared. So as the denominator is 50.2. And then so when I get 45 squared divided by the denominator, that's going to go ahead and give us 40.3 rads per second squared. That will be our angular acceleration. So I'm going to go ahead and write that here as our answer. 40.3 rads per second squared. Alright, great. So that takes care of part A of this problem. Let's go ahead and move along now to part B. In part B, they ask you, find the moment of inertia of the arm and the ball. Alright, so let's go ahead and do that. Now their shapes are slightly different. Let's start with the ball. Moment of inertia of the ball has all the center on the outside. Here's the axis of rotation, and there's nothing in between. So for the ball, the moment of inertia is going to be just mass times radius squared. For the arm though, it's a rod. So for that one, let's go back a couple of slides and you'll see where I get the 1/3 m times r square, or L square I should say. And here it is, it's a rod. So it is 1/3 m times L square. That's the formula for that, because it's an arm. The catapult is basically an arm. So I'm going to put C for catapult. It's going to be 1/3 the mass of it times the r squared. Alright, so now all we got to do is plug in the values for this and this and add them together to get the total moment of inertia. Alright, so the moment of inertia of the ball is going to be the mass, which was 20 kilograms, multiplied times the radius, which is 4 meters squared. So it's going to give us 20 times 16. That gives us 320 kilograms times a meter squared. For the arm is 1/3 the mass of the arm. The mass of the arm was 25 kilograms. Same length, 4 meters squared. So it's going to be 25 times 16 divided by 3 gives us 133. We're going to round it up to that. Alright, so in the question they asked the moment of inertia of the arm and the moment of inertia of the ball. So the answer for part B is here. It is, here's for the ball, here's for the arm. Now in part C they said the net torque exerted on the ball and the arm. So what is the total torque? Alright, so part B here. Part C, let's go ahead and solve it here. So torque is equal to inertia times angular acceleration. We have the angular acceleration from the previous problem. It was 40.3. The inertia, we need the total inertia, so we're going to add both of these together. So to give us the torque total. So it's going to be 320 plus 133 kilograms times meters squared, multiplied times the angular acceleration, which is 40.3 rads per second squared. And that's going to go ahead and give us our torque, which is going to be 40.3. We get, better put that again, 320 plus 133 multiplied times 40.3 gives us 18,256 newtons times meter. Alright, so that is the torque that this catapult exerts. Alright, that takes care of problem number 13. Thank you for watching.